auditory task, you can see that the auditory cortex is activated. So this is just a simple task. You can create a more complicated task in order to identify the different areas that are involved for that particular task. Okay? But this is the standard approach of functional MRI. What we want to ask next is that if you know the activation of the brain, can you identify the task the participant performed given that particular activation? So for example, if you know that the brain, these regions in the brain are activated, from this, can you identify that the participant is doing a finger tapping? Or if the visual area is activated, can you see that the participant is seeing some visual stimulation and so on? So this is our primary question. Given a certain pattern of brain activity, which we call as here as just brain state, can we predict or identify its associated behavior? So these are just simple tasks, but for example, recently there is the push, for example, you are watching a movie and then you continuously scan the participants, and then later on, you look at the brain's data and then you try to see what the participant was looking during this particular data. So the reverse process. Okay. So in order to do this, I think you're familiar with, we use support vector machine. So the idea is to use the brain image in order to classify the task the participant is doing. So I think many of you are familiar with this, but let me just put this in the context of brain imaging. So for example, you are given brain images like this, corresponding to task 1, or just use it as class 1, and we label it as just 1. And then you have another set of images given by this, we label it as -1, corresponding to class 2. And then what we usually do is that for that 3-dimensional image, we try to make it into a 1-dimensional vector representation, given this, okay? And then that particular image, if you look at in the vector space, say for example, in a 3-dimensional space, correspond to one point in that space. So one image is one point in the vector space. So therefore, if you have this set of images here, basically they are just points in your hyperdimensional space. So maybe, for example, class 1 will be something like, will be located here, and then class 2 will be located here. And then the goal of support vector machines, as you may have known, is that we want to find this separating hyperplane such that it will separate the two classes into one on that side and the other on the lower side, for example. Such that if we have a new image now, given by this one, then we can project that image into the plane and see, for example, if it is located here, then we can say that that image belongs to class 2. So that is the general idea of support vector machine. And this is what we use in the succeeding experiments that we have. But before I will move forward, so if you remember here, this separating hyperplane is given by this equation, which we can expand into this, which just really represents the weighting of the different features. Okay? The feature here are the voxels in the image. Okay? That element in the image, that's our feature. And then we have this W as the weights, and therefore we can look out into the weights and try to find out which of these set of weights has contributed significant contribution into the classification. So for example, once we identify the separating hyperplane, then we can put back the weights into the image form like this, and then we want to find out here which weight is significant or is contributing significantly to the classification process. And in order to do that, we just basically perform a permutation test. Basically, what we did is just you just permute the labels. Okay? So instead of putting label -1 to the green images, you can permute it, randomize it such that some will have -1 label and some will have +1 label. And then you can train an SVM to classify the permuted labels, and then you will obtain a weight image like this. You repeat the whole process to get several images like this, and then for each voxel, you can now identify the distribution of weights in that particular voxel. So this is our null distribution, and then we now go back to the original weight and try to compare to this distribution. So for example, if the weight value of the original is higher than this threshold, some threshold here, then we say that that weight is significant in the classification. And we put something here. We label it in the image. We do for all of the weights, and we end up with an image of weights that are significant in the classification. And we call this one as our discriminative maps. I will come to this later in how to improve the classification process for our particular problem. So we have now,
Could you explain why the permuted labeling gets improve the significance or detect significant weight?
So basically, the permutation just tells us that given this relationship, so initially we have this original relationship, this one, and then when we do a permutation, it's basically some form of a null hypothesis that even if there's no relationship, these are the weights that we can come up. Even if there is no relationship between the input and the output.
You mean that you train this VM with the different levels?
Yes.
And you construct several models with different, and then you get the activity of the voxel.
The weights in the voxel.
Yeah,
yes.
voxel weight and the distribution
Of that weights
are considered as a
null distribution.
Yeah.
When there is no relation.
Then you classify the activity of the correct levels.
Yes.
I see.
So if the correct level is higher than the most of the null distribution, then we say that that weight is significant.
How many randomization did you use?
Usually 10,000 randomization. 10,000.
So many.
So one thing maybe is that because the feature space is also huge.
Very
Huge for this.
So it took so long.
It will take some time, yes. Okay. So now that we have brain state, we have the support vector machine to classify the different brains. Now let me go to the real-time aspect of it. So this is the real-time fMRI. So as I mentioned earlier, the real-time, when you do fMRI, you scan the participant, and then after the scan, you get all the data, and then analyze that data maybe a week or several weeks or 1 month after. But in real-time fMRI, the key point is that we analyze the data while the participant is still inside the scanner. So for example, once we get one volume of the image, so we acquire one volume of the image, we immediately send it to an analysis system, okay? And then that analysis system will try to process the data, so do some image preprocessing, and then from the process data, we extract some feature values in that process data, and then using that feature value, we present it back to the participant. So one application for this is that if you want the participant to know the activity of one specific brain area, so for example, the motor cortex, so during the scan, then you can extract the activity of the motor cortex here and then feed it back to the participant. Okay, so that's the real-time aspect of all the analysis. The thing is that all the processing that you're performing should be within the sampling time of your scan, which is basically the TR or the repetition time. This is usually around 2 seconds. Okay. So now, with this, one application which is relevant to what we're doing is, once you get an image, then you can have a support vector machine to classify that image immediately so that you can know whether that image belongs to this class or the other. Okay? And that is what we are trying to do here. So this is now the real-time brain state decoding. So it has two phases. The first phase is the training phase, which you can do online. And the second phase is the testing phase or the real-time scan. So basically, we give participants, maybe in this case, you have 3 tasks. One is word generation, where we ask the participant to generate as many words as possible for something inside the house. So for example, chair, television, computer, sala set, among others. And the other one is computation. Okay? Here we ask the participants to, starting from 100, subtract 7 until you reach 0. So you have sequential subtraction. And then finally, this third task is just movement or motion, wherein we just ask the participant to do imagined tapping. So you are not really doing the actual tapping, but you just imagine that you are tapping your fingers. Okay? And then we obtain images for each of these tasks here, and then we train an SBM in order to classify these brain images. Once we have the SBM, we can use that SBM, trained SBM now, for real-time classification. So during the scan, for example, during real-time fMRI scan, we have a series of images here. Then we can enter it into the trained SBM, and we ask the SBM, what is the participant doing given this image? Okay, so we have to predict this one. And this is how it looks like inside the scanner. So here, this is the target pattern, brain activity. So when you say word generation, then the participant should try to make the activity in the brain similar to generating a word. And then to make it challenging, if the SBM said that the current brain state of the participant is the same as the target, this target, then this arrow will move to the right. Okay? So therefore, basically we try to ask the participant to move this arrow to the right by just making sure that whatever is the target brain state, the current brain activity of the participant is the same as the target. Does it make sense?